Welcome to another video as part of the Pavilion video series, Accelerating Modern Data-Driven Applications with Pavilion. I am Kostas Apopoulos, the Chief Field Technology Officer and Worldwide Vice President of Business Development for Pavilion Data. In this video, I'm going to give you an overview of Pavilion and Pavilion's technologies and what makes us unique to help our customers solve some of the most challenging storage-related problems and deliver incredible outcomes to their business. So the agenda for the presentation will be a fewfold. First, I'll start with our focus. I'll spend most of our time in why is our technology unique and different from our software to our enabling hardware, and then show how the industry is taking notice and what problems we're solving, and then, of course, wrap it up. So let's start with our industry and our solution focus is based foundationally on a couple key areas: high performance virtualization and all the things that can do for an ecosystem, as well as high performance databases, whether those are the SQL databases of today, the NoSQL databases, the tick databases, the key value stores, or even high performance file systems that are being used more as a database. So our key focus areas are those key two technology areas that can be applied in many industries, from life sciences to media and entertainment, to the financial sectors, to federal, and everything else in between. So as we like to look at that, the market is really driving a new set of what we'll call hyper-parallel data-centric applications. If you look at the world as it stands today over the last several years, the infrastructure has become more scale out, leveraging virtual infrastructures like Hyper-V and VMware and Docker. And the applications have become more scale out. Well, that's driven a demand for consistent, predictable, scalable high performance with low latency. And of course, to support those two ecosystems, servers have had to scale out. Well, if the infrastructure is scaling out, we like to call that as hyper-parallel. Well, the applications have scaled out, again, hyper-parallel. Well, the servers have become hyper-parallel. Well, shouldn't the storage also scale out? Shouldn't it be hyper-parallel, be able to start small and grow big inside the chassis, so scale in the chassis as well as scale outside the chassis, be able to have multiple controllers, higher bandwidth, support modern protocols, and give the performance of direct attached storage with all the benefits of shared. Well, that is Pavilion, and we have over 17 foundational patents around NVMe and data storage related activities, and many, many more, as well as many, many more pending. So let's get into why is our technology unique and different, and focus first on our software. Pavilion's been on a very foundational journey. It's really about leveraging our hardware platform with our enabling software called the Pavilion HyperOST, and what that journey has taken and what functionality that has improved over time with that same hardware platform. We started in our first release of 2018 of our HyperOST version 1.0, which was primarily a block storage device that supported Ethernet and the protocols NVMe-TCP and NVMe-RoCE. In 2019, we enhanced that exact same hardware platform by leveraging our 2.0 version of our software that brought in standalone file and object. What we mean by standalone is every one of our 20 controllers could run its own namespace. And we brought in the protocol NVMe RDMA that brought in InfiniBand. We enabled a couple more Ethernet protocols of iSCSI and, of course, NFS and S3 to support our standalone file and object, all on the same current hardware platform. There have also been material performance enhancements to the base foundational software. And then in 2021, we announced and released a new version of our software, 3.0, which brought in the ability to do containerization and run other things on our controller other than what it was originally designed to do, plain block storage. We also introduced a functionality that allows us to not just run other software, but dynamically run in configurable functions that could fire up and run on every one of our controllers. Well, the two key applications that started in our containerization model was our global namespace for file and our global namespace for object. We then introduced our multi-chassis scale-out. So in that global namespace for file and object, which could be a namespace across a single controller or multiple controllers across multiple chassis. We also brought in the protocols of NFS RDMA, our PHFS client, which is our high-performance file client, and many plugins, as well as the ability to tier from our file system to something externally. So that same hardware platform in 2018 has been materially enhanced and developed into a much broader portfolio of a data platform solution that enables block, file, and object. And of course, there's many things to come as we move into our next generation software and beyond. So Pavilion is the most flexible, high-performance storage platform, whether that's block, fast object, fast file, or being an enabler for an external file system like SpectrumScale, BGFS, or Lustre. It's not just performance density, but flexible performance density, and do that at all market competitive pricing. So as we look up the upper right-hand corner, we can be the block storage behind somebody else's file system, like SpectrumScale, BGFS, or Lustre. In the bottom left, we can be the fast object storage ecosystem leveraging our software, or a very, very fast high-performance file system leveraging our file protocol layer called PHFS. And our object leverages our software called PDS3. And these enable many, many applications from the block storage, traditional applications like a SQL Server or running VMware, but also the new modern applications like scale-out databases like MongoDB or Cassandra or Elastic that can leverage block storage as they scale out their applications, as well as really high-performance analytics databases like maybe an OmniSci, or scale-out applications and databases like a Splunk. In external high-performance file systems, we also do really well supporting applications from Spark to TensorFlow to KDB to Hadoop and Graphistry with a log analytics application. To over and fast object, everything's again from Spark and TensorFlow and Cribble and Veeam and Elastic, all sorts of things that we can support because of our ability to not just do object, but high performance object. We really shine in anything that requires high speed ingest, whether that's high speed sensors or device ingest, or applications that are latency sensitive for writes as well as reads. So we give this flexibility of deployment with best in every class performance density. So we give the capability of our customers to bring your own file system, use our file system, use our block, or use our object, the epitome of flexibility. If we're running block protocol, we support the protocols NVMe-TCP, NVMe-RoCE, and iSCSI, our Ethernet protocols, and NVMe RDMA, which is an InfiniBand protocol. In object, we support S3 and some plugins for object, as well as in file. We support many, many protocols and give ultimate flexibility to the host, whether that is NFS v3, v4, or NFS RDMA, whether that is our PHFS client for really high performance, or SMB and SMB-Direct, all supporting file, whether that's connecting to a single one of our chassis as a global namespace, or multiples of our chassis as a global namespace. Well, in our version 3.0 that we released last year, we introduced a high-performance file system for file and object. And that enables us to be able to have multiple controllers participate in a namespace. So for example, a whole system of Pavilion could be a file namespace or a PHFS global namespace. Could be an object global namespace, or it could be a mixed environment of file and object. It's not limited to one single chassis or the controllers in one chassis. We can span multiple chassis to have a global namespace across controllers in one chassis to controllers in another chassis, whether that's file or object or mixing the two together. So as I've mentioned, we support block, file, and object on the same platform, giving us ultimate and flexibility of deployment. We could actually support block on the same platform as you're supporting a global namespace for file and object, and in multiple protocols of block. And if you want to get really crazy, in a global namespace across multiple chassis, we can also support block, file, and object, storage in a block perspective, global namespaces, as well as an external file system leveraging SpectrumScale, Lustre, or BGFS. The ultimate in flexibility. When we look at our multi-client options and interoperability for file, we have the ultimate flexibility. If we were to take a single box or multiple boxes and create a namespace or a global namespace, whichever one we choose, we support many, many client-side protocols. The clients all could be the same client, NFS v3, NFS v4. They could be NFS RDMA. They could be our PHFS client. They could be a Spark client, Hadoop client, or you can intermix those protocols from the host. The ultimate in flexibility, the most flexible hyper-parallel file. So our architecture from a manageability and a fundamental philosophy is a concept of a data plane and a control plane. It enables us to have a manageable environment that enables scalability and ease of use. So a little peek into our software. It's very powerful, but it's simple. Here's our web-based dashboard. Gives you an overview of the platform, health. You can drill down into the management, the controllers, the drives, the fans, the PDUs. Give a characteristic of our storage consumption or capacities, all sorts of high level. Of course, we can drill down to each one of those. Just another quick view, we can look at the system health and we can see how will the status of each one of the drives, the controllers, the fans, and everything. Gives you a graphical view that you can click on and drill down into the health of each one of the pieces and many, many features in between the two slides. Our application and everything you see in our user interface is built around our API, an API-first approach, of which we expose that API for users to leverage themselves. Each one of these I'm showing is a multi-page document that we share with our customers and partners that can show how to use the APIs, for example, for OpenStack, for Kubernetes, to run our CSI driver for Kubernetes, the vCenter plugin for VMware, our REST API, our command line interface, or our Python library, or a Redfish Swordfish reference guide, and everything in between. We have many ecosystem integrations and management system ecosystem integrations from Windows, and we support NVMe-TCP and NVMe-RoCE drivers for Windows. In VMware, we have a vCenter plugin. Of course, we support NVMe-over-RoCE and NVMe-TCP in VMware 7.0, as well as NFS and iSCSI. We have integration into the VMware Cloud Foundry and Tanzu, OpenStack, a Cinder and Nova driver, Kubernetes, a CSI driver, and we have integrations into management ecosystems or reporting ecosystems like Graphite and Grafana. So let's switch gears from our software and why it's unique and different to our enabling hardware. Our hardware is fundamentally different than anybody else on the planet. We look more like a network switch than we do a storage device. So when we built our device, we created it looking like the concept of a network switch, where we have an internal, low latency, cut-through network that connects every one of the round things in the top, our multiple storage controllers, as well as every one of our drives. So an any-to-any connectivity between every storage controller to every drive. And we have a lot of software and not just management software, but key integration software to create a distributed, shared, persistent memory that allows every single one of our controllers to know about every one of our drives and all the metadata about everything in our system. That fundamental platform has manifested itself to the platform we have today in our unique architecture. As I mentioned, take that block diagram I showed, which is a very unique network-based, network-centric design, and put that into an application of a Pavilion hardware platform. We're fundamentally built around a 6.1 terabit PCIe network switch, highlighted in the middle on the right. We also have the capability of having up to 72 2.5-inch U.2 NVMe drives. Every one of those drives can be connected to every one of our 20 independent storage controllers. If you look on the right, the picture on the right, you can see the cards that are horizontal. There's 5 on the top, 5 on the bottom. Those are our line cards. If you map that to the picture on the left, it's a rear view of our system. You can see the back of each one of our line cards where the network ports are. A line card has the capability of 2 independent storage controllers each. They're not dual controllers. They're 2 independent controllers. They have their own CPU, their own memory, and their own network. Well, each one of those cards has up to 4 Ethernet or InfiniBand ports. We can have up to 40 100 gig Ethernet or InfiniBand ports, or we actually have a line card that has a 200 gig InfiniBand port. All of that packed into 4 rack units. The drives on the left could be anywhere from, we now support 30 terabyte drives to the 15s, the 7.6, and down into the 3.2 drives. So that platform you're seeing on the right could be 20 controllers and up to 2.2 petabytes raw in 4 rack units. And I'll share the performance in a little bit. Let's just give a tease, and 20 million IOPS. How do we do all that? Any one of those controllers could talk to any one of those drives. We have a concept of a cashless, tierless architecture because we leverage DMA technology, direct memory access technologies from every one of our controllers to every one of the drives. We don't need a tier. A tier may slow us down because we write directly to write and read directly from every single one of those drives at nanosecond speeds. We also speak RDMA technologies out to the host, so in microsecond technology or microsecond speeds. And as Satish, one of our founders, says, our softwares have many software patents that takes unfair advantage of our hardware. We also have the ability, if you're leveraging our file and object, to tier outside of our box onto something NFS and S3, i.e. cheap and deep spinning disks. So not just performance, not just density, but unrivaled performance density in a very unique and different hardware architecture. Well, that HyperOST that I spoke about, which is our operating system, is built from the ground up to support NVMe and NVMe-over-Fabric. Our platform was fundamentally designed to run NVMe drives and leverage the protocol NVMe-over-Fabric. We've never had a drive in there that doesn't support NVMe. Every one of those controllers, up to 20 controllers, runs a separate instance of our HyperOST. So it runs our base platform, but also has the ability to run a container of an application on every one of those controllers. It gives us the ultimate scalability to have block, file, and object on different controllers. And all of those controllers talk with each other from a separate internal management ecosystem. When they talk data, they talk through our PCIe fabric. So that separation of a data plane and a control plane. Well, you may say, 20 controllers, do I really need all those 20 million IOPS? And the answer is you may not. And you don't have to start with 20 million IOPS, right? You could start with the smallest one of our systems is still in our 4 rack units, but you could start with 18 of our drives and 2 of our line cards with 4 controllers. And maybe you just want to run block. Then you may decide that I need a little more performance and I want to run some file. And then maybe I want to run, I needed more capacity. I can just add more capacity, but I have enough performance. You can see how I can scale performance and capacity independent of each other and add storage functionality as I grow. So you don't have to start big. You can start small and scale inside the box. We give that every time we scale, it's linear scalability with consistent, predictable, scalable high performance with low latency, whether that's block, file, or object. So we can scale in place as your business grows. We have some unique high availability features. Because of our multi-controller architecture, we have the ability for controllers to fail, maybe controller 1 failed to controller 2, 2 to 3 to 4 to 5. So each controller can be running active, but also could be standby for another controller. Kind of a round robin perspective. But because we have multiple controllers, we have the unique ability to do something we'll call controller RAID, that you could have a controller that's dedicated to no workload, but is the failover controller for, say, 4 other controllers. Well, what does that mean? I may be wasting a controller. Well, the reality is, in a round robin or any typical dual controller architecture out there today, but in our case, a round robin, you got to be careful of how much workload is on every one of those controllers. If controller 1 has 80% workload and controller 2 has 80% workload, when 1 fails to 2, you could be running in a less than optimal configuration. But by using the controller RAID, you can take every one of those controllers and run them up to 80, 90%, because in the case of a failure, it'll fail over to a controller that is running no workload. Very unique to Pavilion. We also have support data assurance technologies like T10-DIF. Something unique to Pavilion is something called metadata version that has a patent pending that protects against drive firmware drops. As drives get bigger and the performance gets more intense, they can drop writes. In other words, as the operating system writes to the drive says, I have it. Well, what happens if they don't destage that to their own internal cache? Not a Pavilion cache. This problem, by the way, I'm describing is for every kind of drive from every single vendor with every single storage platform. But we put software to take a version of when it's written and make sure when we read it, that same version comes back. So we've given another layer of data protection called metadata versioning. So what does this all manifest itself into? The Pavilion HyperOST 3.0 performance expectations in that single storage platform of 4 rack units and up to 2 petabytes raw. We have the flexibility to support multiple storage types at single platform. If we were to run the whole platform as block, remember it doesn't have to be all block, but in these use cases, I'm going to share the whole platform as block. We can deliver 20 million read IOPS, 5 million write IOPS at 100 microsecond read latency and 25 microsecond write latency. From a throughput perspective, it's 120 gigabytes a second read and 90 gigabytes a second write. Impressive block performance. Equally impressive is its file and object performance. 78 gigabytes a second read and 56 gigabytes a second write from file, 52 and 28 for object. In that file and object, those can be clustered together in multiple chassis, and as you scale a chassis, the performance will linearly scale. Just like in the block mode or file or whatever, as you add controllers inside the box, the scale is linear. So our file and object global namespace can be clustered with multiple systems and delivering linear scalability. So let's look at that scalability from a file perspective. So for example, I mentioned that one of our boxes, if running file, could be 78 gigabytes a second read and 56 gigabytes a second write. Well, in that spirit of I may not need that, now I want to grow into something. Well, that's great. You can use a quarter of our system as an example. And a quarter of our system will deliver 19.5 gigabytes a second read and 14 gigabytes a second write and 500 terabytes of raw capacity. By the way, 1/4 of our box in that performance is more than a FlashBlade from Pure and more than an Isilon box, even their new box. And that's 1/4 of our box. You could then add another 1/4, and you've doubled the performance. You see on the top, the scale up and the 39 and 20, it's doubling the read, doubling the write, doubles the capacity. Add another quarter, add another quarter. You can see how you can start small and scale inside the box. Well, that scaling is not limited to inside the box. As I mentioned, we can scale outside of our box. So if we had that, I'm going to give an example of a full box in this scenario, 78 gigabytes a second read, 56 gigabytes a second write, and 2 petabytes. You add a second box and add that to the global namespace. You just doubled the read, doubled the write, doubled the capacity. Triple, quadruple. I'm giving you an example of 8 boxes. This is what we've tested up to 8 boxes. In those 8 boxes for file would be 624 gigabytes a second read, 448 gigabytes a second write, 16 petabytes of usable capacity in 32 rack units. That's two-thirds, a little more than two-thirds a rack. If that were to be configured at object, the performance would be a little bit less, and you can see those numbers there, because the per object, per chassis object is slightly less than the file. So very, very scalable. Scale inside the box as well as scale outside. So what does all that performance help you do? Well, in two key use cases for us is what we perform really well in high-performance databases, whether that's the traditional databases or it's the scale-out databases. We also do really well in high-performance virtualized environments with VMware as an example. And equally good is those databases inside of VMware on Pavilion. So applications run better on Pavilion. An example of that is MySQL. Running in a bare metal server leveraging our platform, we've seen 2 times the queries per second, 7 times the transactions per second at half the latency. Take that same environment and stick it inside of VMware, leveraging the same hardware. It's 1.8 times the queries per second, 6 times the transaction per second at less than 60% the latency. PostgreSQL, 1.5 times the queries per second at 67% the latency, and a little over 1.13x the queries per second at less than 90% the latency in VMware. SQL Server, less than 200 microsecond latency for reads and writes, and similar same performance for virtualized VMware environments. I'm going to share some examples of successes for SQL Server as a result of our customers are seeing impressive results with SQL Server. And there are many other tests that we're running and we can share. Just reach out to us for other applications we have tested. So as we look at that, and I said VMware does really, really well, what we're seeing, especially in databases, is people can take their databases that they typically were a little nervous, or their workloads that were a little nervous of running inside of VMware because of performance, and put that environment inside of VMware now because of the technology of NVMe-over-Fabric from VMware, and in particular the performance of Pavilion. Scott Sinclair from the Enterprise Strategy Group has said, with the release of vSphere 7, VMware takes NVMe-over-Fabric mainstream. Remember, we're one of the founding patents of NVMe-over-Fabric. We've been there before it started. So Pavilion enables VMware environments to deliver, whether that's ESX and leveraging VMs or leveraging containers. We support both NVMe-over-Fabric RoCE and TCP from VMware to Pavilion, and you see our overall specs to our platform. So an incredible platform for VMware. Again, we see similar same performance of people running their applications outside of VMware to inside of VMware. Actually, some of the VMware testing was done by Mellanox, now NVIDIA, in Israel. And they did testing with a Pavilion box, and they tested the protocol iSCSI versus NVMe-over-Fabric RoCE. And this was a comparison of like hardware to like hardware, all on a Pavilion storage array. And the results were from a read 2 times the read IOPS at half the latency, leveraging the exact same hardware, iSCSI to NVMe-over-Fabric RoCE. From a write perspective, 1.5 times the write IOPS at 61% the latency. That allows us to run 2 times the virtual machines, or maybe cut the cost of 50%, or run more virtual machines at half the latency, or do 2 times the IOs at half the latency with the same number of virtual machines. Or it can really increase the bandwidth, which is about 143% increase in bandwidth for AI, machine learning, deep learning, or analytics type workloads. So that question earlier, what can you do with all that performance in block? We have a large European research organization that we've had an implementation for 2 years. It was when the implementation before, to win the deal, we had to compete on very high IOPS with low latency. It came down to 2 vendors, us and another vendor. and it was pure storage, right? And the quote for us took 1.5 Pavilion box to deliver the performance characteristics. It took pure 16 arrays. We were 10 times faster, 6 times smaller, and 20x less cost. They've now put many, many more workloads, including VDI, SQL Server, and Greenplum, all running in a VMware environment. They're now adding Object with VMware Tanzu and Cloud Foundry, all on the same platforms. As I mentioned, applications like SQL Server run really, really well on Pavilion. So we unleash the power of Windows and SQL Server through our super high bandwidth and ultra low latency, whether that's large block size, small block size, read or write. And if you look at it from a SQL Server perspective, the number one most important storage attribute to materially affect SQL Server storage performance is latency. And Pavilion delivers latency, whether that's in a bare metal environments running Windows, leveraging our certified drivers from NVMe-TCP to NVMe-RoCE, or whether that's inside of a VMware ecosystem, leveraging NVMe-RoCE or NVMe-TCP. All VMware certified, all Windows certified. Incredible performance and incredible scale. So why does that latency matter in SQL Server? Well, we'll call that enabling effect. So if transactions can commit faster because of lower latency, that allows more transactions to happen, obviously, which enables more concurrency in the database and the Windows SQL Server environment, which can either allow more users on the same database or more databases on the same server, or both, by the way, which means better hardware and software utilization, which of course means a lower TCO. So what is the financial effect to that? Because of our ultra low latency, our technology allows VMware, as an example, and SQL Server, so SQL Server's memory to refresh faster, which enables you to have less memory in the SQL Server buffer pool. Well, by doing that, you can put more SQL servers on every VM host. And what we've seen, that reduction with Pavilion is 30 to 50% less in SQL Server and VMware cost because of our ultra low latency. So examples of our SQL Server acceleration, we have customers doing everything as from running in a shared environment with NVMe-over-Fabric. In fact, we also have a customer that's direct to connecting really massive, 4 very massive SQL servers to each Pavilion box and leveraging it as external storage. Not Fabric attached, just NVMe-over-Fabric attached, but not network attached. So you can use it in a very flexible way. And they saw the same or similar performance as what they had with the drives physically in the server. We have other customers leveraging it as what it was designed for, a shared storage in a NVMe-over-Fabric networking fabric perspective. And again, similar or same performance as what they had in DAS. So David Klee is the founder and from HyperOST Technologies and a very, very deep SQL Server expert. A quote from him: "Pavilion storage underneath my SQL servers is the first SAN to completely move the primary bottleneck to database performance away and above the storage device itself. Now my bottleneck is in performance is where it should be, in the database design and the application code. Storage is no longer the bottleneck." That same ecosystem could be run in a VMware environment and running SQL Server inside. I showed that before. Again, quote from David Klee: "SQL Server on VMware comprises the bulk of the servers that we see in the wild. The unmatched performance that Pavilion offers allows me to reduce my SQL Server memory footprint, pack more SQL servers on every host, while improving performance and squeezing more out of my expensive SQL Server license. Everybody wins." So if you're interested, reach out to Pavilion. We have a tool that leverages and provides an ROI analysis or TCO analysis of running SQL Server inside of VMware and allows you to plug in your current environments and show what the potential host, SQL Server, and VMware license savings would be. We also have examples of running that on some of the competition based upon their performance. Again, this does not factor in the storage cost. This is purely the software savings for leveraging a Pavilion storage array versus what you have today because of our low latency. What we've seen in these cases, a lot of times the savings of the VMware licensing costs and the SQL licensing costs alone could fund the purchase of a brand new storage array or many storage arrays, depending how big you are. So what can you do all that performance in file? The SQL Server thing is block. And in file, here's an example in the NVIDIA GPUDirect world, which we support. Relative to public available information, one of the competitors, in their GPUDirect testing published by NVIDIA, is the first competitor. We were 110% their read, almost 400% their write, at 9% their latency, at less than half the physical space. Another competitor, we were 117% their read, 170% their write, at 73% their latency, at less than 70% the rack units. Also with key environments like a life science, give an example of a cryo-EM, things that require high-speed ingest or high-speed read and write at the same time. So for example, you may have these cryo-EM microscopes that are ingesting data, by the way, that are mostly a Windows environment, right? Ingesting data. You then have maybe a Linux environment doing high-speed processing to really transform the data, do some cleaning up of the data. And then you have high-speed analysis, whether that's in Windows or Linux. So it enables improved workflow and more improved workflow concurrency, better microscope utilization, better cycle time between tests, and better processing times. Because in typical environments today, one device copies the data somewhere, then somebody moves the data from there somewhere else to analysis, then moves the data somewhere else. Put the data one place, do the analysis all in one place, and improve the workflow. We have a challenge to all the storage vendors is, be honest, share all your information. Here's an example. You go on a website, one of the storage vendor X says they do 300 gigabytes a second. Well, by the way, that takes 48 rack units to do that. Another vendor says they do 350 gigabytes a second. By the way, that takes 88 rack units to do that. Pavilion, look at what we share. Our gigabytes per second read, our write IOPS, our read IOPS, our latency, read and write. We deliver in 4 rack units, in other words, less than 7 inches, block, file, and object. So I asked the question of vendors as you're comparing us to other people is what tool did they use to generate those tests? Was it FIO? Was it GDSIO? Was it disk speed? Should we just pick read or write, or should we share everything? Should we focus on small or large block size? Should vendors get away with just publishing 1 or 2 numbers? If you look at most competitors' website, one of them will say they do incredible latency, 1 millisecond to 150 microseconds. Was that read? Was that write? What block size was that? What about your throughput? What about your IOPS? So let's be intellectually honest. And you as customers and partners, ask those vendors those questions. Are we comparing apples to apples? Is it block? Is it file? Is it object? How many rack units does it take to deliver that? Again, think of that. One vendor says, I do 300 gigabytes a second. That's amazing. That's in a full rack. You know, developed a tool called the Storage Normalizer that we can share with you that charts this out and compares the competition. It gives you a form to fill out. All the information you know about each one of those vendors or in your research, go ask those questions. It comes pre-filled out with Pavilion's numbers, and the charts will automatically appear. That can be found as part of our blog. You can see the link below. The other area for us is I said you don't have to start big, you can start small. Here's some examples of set configurations that you can do. Starting on the right, we call those more of performance or capacity optimized, right? I only need a few controllers and 1 drive, so you can be a small, a medium, or maybe have max performance with medium capacity. Gives you all the different options, and you see below each one what performance you can expect from each one of those configurations. That's intellectual honesty from a vendor out in the marketplace. So with all this I've talked about today and all of our results, the industry is taking notice. Gartner is an example. Quote from them: next generation data-centric workloads like AI, modeling, and simulation require bandwidth, latency, and I/O operations per second performance beyond the capabilities of NVMe technology-enabled, keyword, dual controller scale-up all-flash storage arrays at scale. A Pavilion differentiator. Chris Meller at Blocks and Files: I think Pavilion has given DDN, VAST, and WEC I/O a hard problem as your system's superior hardware architecture accelerates file I/O beyond their limits. Michael Kagan at Supercomputer Show in 2020. He's a CTO of NVIDIA. Some of the words that he said related to me as I listened to the presentation. And by the way, that picture is him with a slide, and you see Pavilion highlighted over there. He said, high performance computing requires high performance I/O. Well, that's definitely Pavilion. He also said the rule is simple. The higher the processing power the computer element has, the more data it can process, hence faster data delivery is required. Well, Pavilion helps that. He specifically called out Pavilion. Pavilion, performance improvement for file storage of almost 4 times leveraging GPUDirect storage. That's direct Pavilion. Last thing that I think related to storage was storage access is yet another bottleneck that needs to be resolved. Well, Pavilion resolved that bottleneck. As we look at GPUDirect storage and testing that we did with NVIDIA and published results that are out in the marketplace today, Pavilion's performance advantage to the competition. The purple number on the left is one vendor. A purple number on the black number on the right is another vendor. Purple is VAST. The black is WECA. In that NVIDIA GPU testing, which you can find out on the internet, is our read bandwidth was 110% VAST at 9% the latency, at 40% the rack units, 400% the write bandwidth, at 47% the write latency, and they don't support block. We do them in both. WECA, 117%, 73% the latency, 67% the rack units, 169% the write bandwidth. They didn't publish the write latency, no support for block. I always ask questions of every vendor back when that storage normalizer. If a vendor doesn't publish numbers, there's probably a reason why. So in summary, we stand out from the pack for any applications or solutions that have the need for speed. It's our performance, it's our density, it's our scalability, it's our flexibility. Whether that's for high performance virtualized environments, high performance databases, particular SQL Server or MySQL or Cassandra or Elastic, storage for parallel file systems like SpectrumScale, Lustre, BGFS, great storage for VMware, whether that's for RoCE or TCP, incredible high performance object, incredible high performance file for workloads for AI, machine learning, deep learning, with support for NVIDIA GPUDirect storage for block and file. We like to say it's back to shared storage from DAS, where a lot of people for some of these scale out apps put drives back in their servers and scaled them out. Now when you need storage, you have to add another server, so you have to add compute. If you need more compute, you have to add more storage. We give similar or same performance, and sometimes better, in our environment versus direct attached storage natively in the servers. So for fast file, fast object, fast block, many use cases. Pavilion enables applications anywhere from TensorFlow to Lustre to Splunk to SQL Server to Greenplum to MongoDB to VMware to provide solutions for things like AI, machine learning, data analytics, high-speed databases, sensor ingest, high-frequency trading, or a virtual infrastructure in general. But fundamentally, we deliver cost-effective outcomes to the business. And the reason we do that is we help your applications run faster, perform more consistently, and scale larger. Thank you. Thank you for watching this video as part of the Pavilion video series. If you want to learn more about this topic or others, check out our other videos at www.pavilion.io. You can also reach out to us via email at info@pavilion.io, or you can always call us on the phone. We'd love to talk to you about how Pavilion can help you solve some of your most challenging storage-related problems and help you deliver incredible business outcomes to your customers. Thank you.